Before moving on, there's a couple things about the free particle I wanted to talk about. So just a reminder, here's the free particle. So the general solutions, again, are oscillatory. We prefer to use the complex oscillatory solution. And when you add that with the time evolution from the Schrodinger equation, we get these two waves. One that we look at is propagating in the positive direction, and one propagating in the negative direction. Now, if you look at just this free particle, this state, and ask what the theoretical speed is, okay, we did this in class, and we get this here. And again, this is just by looking at this and saying, well, whenever I have x minus this form, okay, I know that that's something that's propagating, in this case, propagating to the right. And so by just looking here, just by inspection, you can get here that the velocity, in this case, for this wave is h bar k over 2m. And so let's just think real quick, all right, if we look here at our classically, so classically we're going to say 1/2 mv squared is equal to my kinetic energy. And so I can solve that for my velocity classical, and we get something along the lines of this, so 2e over m square rooted. And so if I take that and plug in what my energy is, so again, we know that the energy for one of these guys is h bar squared k squared over 2m. And so if I plug that in over here, I get 2 times h bar squared k squared over 2m. And of course, this is all divided by m. So this is 2e divided by m, the square root of all of that. All right, and so if I get out of that, what I come out with, the 2's cancel, and I get really nicely h bar k over m from that. And we call that the classical velocity. And so Griffiths calls this other one the quantum velocity. And so this is a problem that we have, okay, that these two velocities don't match up. And so we want to investigate this a little bit. And basically, one sort of way to think about this is, again, this wave function, as we discussed, is not a physical wave function, so it can't describe a particle. All right, so that's why these mismatch. But it'd be nice if we could find a way to sort of find this particle in here somewhere. And so looking at here, this is how we're going to do it. So again, the general solution is going to be a linear combination of these free particle solutions. And so we talked a little bit about this last time. And so we get this integral, which again is very similar to the integral we set up before. So this phi of k, the momentum space wave function, is very similar to our CNs. And then here, this we've sort of connected in here the energy eigenfunction, that's the e to the ikx part, along with the time evolution. And so instead of it being a discrete sum like we had for the infinite square well, now we have this nice integral. And so this function is our best representation of a wave packet. And so what we want to say is it possible, can we find, so if this thing does represent a particle, can we try to find this particle's velocity? And so if I look at this here, what I can do is similar to what I did in that last one. If I pull out the k, okay, we get a shape that kind of looks like this, which if you look at this, you say, oh, hey, look at this. I get e minus v times t, all right? And so obviously the velocity must be this thing in here. Okay, now the problem with that is that's the velocity with one of the individual free particle states, one of the individual momentum states. And so that's basically just the same thing we just kind of solved for a second ago. All right, and so the thing is here, since we're integrating over a large number of these k's, okay, then we can't just say that that's the velocity. All right, and so that's where the problem comes in. I think with this next derivation we're going to do, I think part of the problem is people, sort of don't really see the need as to why do I even do this derivation. And that need is right here. Okay, I'm adding up a whole bunch of these plane waves, and so yeah, so this is sort of how we would call the velocity of each one of these plane waves, but we don't know how to sort of look at the velocity of the whole, and that's what we're going to try to do with this next calculation. All right, so let's go through this. Again, this is a very tricky calculation, and I'm going to go through it. Hopefully that helps a little bit, but I think it's really useful to go through this yourself. And so here Griffiths writes out the general form of our wave function, and just to make life a little bit easier, over here in the time evolution piece, he just writes it omega. We've done this ourselves a few times. Remember, omega is just En over h bar. And we're going to talk about a situation where we have a momentum space wave function that's very tightly bound about one point k sub 0. And so we're going to use this. This is the trick to how this is all going to work for us. And Griffiths argues that, well, basically, if you don't have a momentum space wave function that's really tight around k sub naught, things are going to spread out very, very fast, and it's not a very good representation of a particle. And so the trick here is that we take this omega and we write it out as a Taylor expansion. So it basically only considers points really near that k sub 0. And so here we have omega naught, okay, the constant term, that's, that omega naught is at the point k is equal to k sub 0. Then we have d omega dk, again, that's going to be at the point k is equal to k0. And then we got this k minus k naught. And so this is our Taylor expansion of this here. We only keep the first two terms. And we make a substitution. We call this d omega dk v sub g. We're going to see that this ends up being our velocity. And so he plugs this in here for the omega times t. So omega naught times t plus vg k minus k0 times t. And then basically massages these different terms. The first thing he realizes is that here you have e to the I omega naught t. That does not depend on k, so I pull it outside and try to forget about it. Now next, he writes it out like this. Now what he does is he sort of adds a very special 1. And so he says e to the k naught x times e to the I. Okay, so e to the I k naught x times e to the negative I k naught x is equal to 1. So he introduces it here. So here's the part with the positive, and then the negative part is over here, I to the negative k naught x. And so it gives us two like terms over here. And now this thing does not depend on k, only k naught, which is the constant. So he pulls that out front. And then now here I've got something that's like e to the a times e to the b. Well, that's going to be e to the a plus b. And so he takes that, and if you write that out, it's basically all of this garbage here. So it's I k minus k naught x minus I vg k minus k naught t. And then they've got this term of I times k minus k naught. He pulls that out, and lo and behold, you get this nice form we like, x minus vg times t. Okay, where again, the vg is our d omega dk evaluated at the point k naught. So it is a constant. Okay, it's not something that's changing as I change k. It is a constant. So we're able to write this in the form that leads us to believe that vg is our velocity, and the g stands for group or group velocity. Okay, so we're very happy we get this written in this way here, and vg equals d omega dk. Now if you remember, our omega was our energy divided by h bar. So for us this is h, or just one of the, so yeah, I should just write h bar squared k squared over 2m. And so for us this is h bar k squared over 2m. And what's really nice is if I plug this into our derivative, I get 2 h naught k over 2m. Now remember, this piece is evaluated at k equals k naught, and so I get h bar k naught over m, which is what we would expect our classical velocity to be. If you go back to the beginning, that's sort of what we were hoping to find. All right, and so the key is in this sort of setup here, I get x minus some constant term times t, where in this piece here, the more general form, okay, this piece here changes with k. Okay, and so you're talking about sort of the different k for each individual piece, but here I get the whole formula. I can write it out as some function of x minus some constant times t, okay, which is sort of the goal that we're trying to do. And so we have the group velocity, which is basically the velocity of our whole wave packet, and then the phase velocity, which is the velocity of each individual momentum eigenfunction. All right, and again, I will definitely go through this, ask questions, and we'll talk about this in lecture. One thing, just real quick, just a definition. I think just the word sometimes can throw people. They call about this as our dispersion relationship. And so we've seen dispersion. The example here from the Pink Floyd album cover is the variation in wave speed with wavelength. Well, dispersion is just a way of saying separation of what was once in one place. This is like a slick dictionary definition. And so when they say dispersion, that's what they mean. With our wave packet, sort of everything starts in one place, but as it disperses, okay, it gets sort of fatter and fatter, and you're separating out what was once in one place. And so that's what they're trying to get at with that. And lastly today, we want to talk about our good friend, the Dirac delta function. And so we've mentioned this briefly in class just because people know about it. But here's, I think, a nice definition of the Dirac delta function. There's lots of different definitions. We'll talk about these. And so this is the epsilon version of the Dirac delta function. And so this is some function. So here's my y-axis and my x-axis, like so. Okay, so this function is defined as going from negative epsilon over 2 to positive epsilon over 2 and having a height of 1 over epsilon. All right, so the area in this box, all right, is 1. That's sort of key to us. The area is 1. And our true Dirac delta function, which we'll write this way, is basically this thing where epsilon goes to 0. All right, and so it's a funny thing. It's not really a function, as Griffiths talks about, but it's basically this thing. So if we look over here, it's got 0 width and infinite height. But altogether, it has an area of 1. And it's what we're going to use for different purposes. And so here's a little picture of the Dirac delta function. And so basically the key is if I integrate over all space, the area there is 1. Okay, and so this is going to make it very, it's going to make this Dirac delta function something that's very nice to integrate. All right, and so here's our sort of definition then. It's 0 for anything. So the Dirac delta function of x is 0 for anything that's not 0, then infinite at that point. All right. And what we can also do is move it over. So if I say the Dirac delta function of x minus x0, it's exactly the same thing. It's just now centered at x0 instead of at 0. And the one thing about this is we have this sort of relationship here. Okay, that if I multiply a function, some f of x, this could be anything, so here's just some random function, what the Dirac delta function does, this one here, is it picks out the part of that function that is at that point x sub 0. And the sort of best way to think about it, and one thing that is just useful, is that Dirac delta functions make much more sense if we are using them inside an integral. And so if you get confused, it's just sort of nicer to put it inside an integral. But if I have the integral of f of x times this Dirac delta function, okay, well, what does that do? Well, basically, since I'm integrating over all space and the Dirac delta function is only non-zero at that point x sub 0, then basically all the rest of the parts of the function, okay, over here and over here, are essentially not necessary. And so I can just sort of call my function only centered at that point f of x sub 0. And the delta function is so skinny that basically it's only at one point that function is defined as far as this integral cares. And so since this is a constant, I can pull it outside of my integral, and we know the integral of a Dirac delta function is always 1. And so what this tends to do is give me the function f at that point. And so that's one really big key here, is that integrating a delta function, even though at first it seems scary, is actually one of the easiest things that we can integrate. And then finally, so we're going to talk much more in class about the delta function, but one thing, why delta functions? Why are they useful? Well, one thing is, first of all, this is how you describe something that's basically located at one particular point. All right, so like a charge density. You can use these in electricity and magnetism to describe a point charge, the charge density of a point charge, where all the charge is at one point. Okay, for us, this is going to be the eigenfunction of position, right? And so if your particle really is at sort of one position, then the delta function is how you represent that. So this will be the eigenfunction of position. So these are two very useful things. Now the other thing is, we talked about this a little bit, and we saw that it was really, not too bad to integrate this thing. And so the delta function can be a really great first approximation to other potentials. So this is a potential I've shown you a few times. So this is the potential of, say, a bunch of atoms. And so here's a bunch of nuclei, some one-dimensional nuclei. And if we look from these nuclei at the potential that an electron sees, it looks like these. So these are 1 over r type potentials, and there's basically a bunch of these. And the thing is like for instance, sometimes I'll do calculations in my condensed matter work where I'm trying to sort of get a feel for what this potential looks like. And what I can do is initially, instead of having it be sort of the realistic potentials, I can use sort of a setup of some inverted Dirac delta functions. Okay, so basically that's just negative of the delta function. All right, and so what this does is it gives me a potential that kind of acts like this. Okay, it's a potential that's sort of trying to attract the electron, to these points here, and so it works similar to the real life potential, but it's one that you can usually do your calculations with much faster. And so it's a really great first approximation to other potentials. So that's just some of the usefulness of the delta function. We'll talk much more in class.